Okay. Hi, everyone. Thank you for this invitation. I'm happy to be here to share with you some research work I conducted recently on quantum machine learning. So I'm a professor at Aix-Marseille University and a member of the machine learning team. So my background is classical background, but I started working on connection between quantum computing and machine learning about 5 years ago in the framework of collaboration with other colleagues, Giuseppe and other colleagues. And today my talk, I will show you a general introduction of this field of research, quantum machine learning, and I will illustrate some interactions between quantum computing and machine learning. I will not have the time to show all this interaction, but I will choose two specific interactions and I will enter into the details of these interactions, okay? And feel free to interrupt me and ask me any question. Okay, so quantum machine learning is a relatively recent field of research, as you know, at the intersection between quantum computing and machine learning. And the interest in this field is in the two directions. First, from quantum computing to machine learning. And in general, the goal here is to design a quantum enhanced or quantum inspired machine learning algorithm. So the idea here is to take advantage using concepts and using algorithms known in the field of quantum computing and try to see how these algorithms and concepts can improve our machine learning, our research in the machine learning field. Okay, but there is also interest on applied machine learning and in general classical machine learning to also address and solve problem in quantum computing and the quantum information. Okay. If you would like to know more about this field of research, maybe you can start by this survey paper published in Nature in 2017. So the paper shows clearly different kind of interaction and different also contribution in this field. But it is important to know that this field of research is growing quickly. So here in this figure, there is here the growth. So the curve is the number of published papers on quantum machine learning from 2018 to 2022. And as you can see, the number of paper now has increased about 5 times. So in some sense, you need a more recent survey now on the field quantum machine learning, but because there are a lot of works which have been done these recent years. Okay. One also can ask the question where the research on quantum machine learning is located. Since the field of research is recent, it is not easy to have a clear idea about where this research is located. But here I have the figure about top 10 countries producing quantum computing and quantum communication papers. Why I chose this figure? Because in general, research centers working on the field of quantum computing or quantum communication also have now researchers and have groups working on quantum machine learning. So in North America, USA and Canada, for example, Google have a quantum artificial intelligence lab. In Asia, mainly China, Japan, and also India, and also in Europe, United Kingdom, France, Germany, Italy. If you would like to categorize the research on this field of quantum machine learning, it can be done into 4 categories, depending on the nature of the data and the nature of the algorithm. So here, as you can see, we have type of data, which can be classical and can be also quantum. And here we have the type of algorithm, which can be classical and also quantum. And depending on this combination, we can find a subfield of research in quantum machine learning. Most of the research are in the setting of classical data and quantum algorithm. Indeed, in this setting, we have a lot of data, classical data. Also, there are a lot of problems, and one can ask the question, if we use quantum algorithms, we can improve the performance of classical algorithm. In general, in this field of research, people try to use already known quantum algorithms that have advantage compared to the classical algorithm, and see how to adapt and how to apply this algorithm in the context of machine learning. For example, one of the famous algorithm in the field quantum computing is Grover search, as Giuseppe mentioned this morning. The goal of the algorithm is to find an element in a list of elements, and we know that the performance of the algorithm is better than the performance of the classical algorithm. And so the question after that, can we use this search algorithm in the context of machine learning? And if we can, what kind of advantage we can have in the context of machine learning? I will go back to this Grover algorithm in the second part of my talk, because I will show how to apply it to solve a classification problem. Okay? There is also an interest in QC. So here the data are quantum and the algorithm is classical. And in general here, we have problems in quantum computing and quantum information. So we have quantum data, and after that we can try to see if we can address this problem using a classical algorithm. One is here as illustration. One known problem is quantum separability or quantum entanglement detection. So quantum entanglement is a specific feature and an important feature in quantum computing, and detecting entanglement is a difficult task. So here in the figure we have different the quantum states, and we have the class of entangled quantum state and the class of separable quantum state. And when you have entanglement, we have some specific correlation that cannot be captured using classical information techniques. Okay. So one possible way to address this problem using machine learning is to generate a lot of data, quantum data in this case, and after that to separate these two classes so it can be seen as a classification problem. One can try to find this separation using a machine learning algorithm classifier. Some sense. So in this case we have as input density matrices quantum states. Okay, so this is quantum data, and we will use a classifier, classical machine learning algorithm to solve the problem. Okay, we can also be in the situation where data are quantum and also algorithm is quantum. So this is the fully quantum setting, and we did work on this category with Giuseppe and our PhD student Baltazar Casale on quantum bandits. So the bandits are very known algorithms and the setting of reinforcement learning, and the goal is to find the best strategy. So here, for example, in general, to illustrate this kind of algorithms, we consider the bandit problem. So we have many cache machines like that, and after that we have a player, and the player should find the best strategy. What is the meaning of best strategy? What is the arms that he will play, the sequence of arms that he will play that maximize the game. Okay, so there are many classical strategies, and we try to have a quantum perspective in this for this problem, and use quantum superposition. This is why I took this figure, which is not related to quantum, but it mentioned clearly the idea we had to solve this problem. So it is like we have an agent, and we can play by using quantum superposition. We can play all the machine at the same time, and we can show after that we are able to have beta guarantees in this case. Okay. Okay, so here in this situation, we have that the agent can play different machine at the same time, so superposition, so quantum, and after that, each time he will play, we will have a reward. The reward can be positive and negative, but the reward in our setting can be also in a superposition. So we have both the agent and the reward. Our environment are in superposition, are quantum, and we are on the fully quantum setting. Okay. There is also some research work where the data are classical and the algorithms are classical, and we can also say that this research work belongs to the field of quantum machine learning. So I will start by this part, okay, to show you what kind of research we can conduct in this setting. And the second part of my talk will be on CQ, so classical data and quantum algorithm. Okay? Any question? Classical data is data provided by a classical way of computation. So if we have all the classical data we have now, this is data are obtained and we can use them when you are using a classical computer. So this is classical data. Quantum data are data provided by quantum system. But it is true that in this work on in this field of research, I would like QC, there are some work that consider that we have quantum data provided from quantum resources, okay? But also we can consider classical representation of quantum data, okay? So in classical representation, for example, Giuseppe mentioned in this morning density matrices. So this is our matrices that describe quantum states that have some properties like positivity, and the trace should be equal to 1. One can consider a classical algorithm which will which can be applied to data of this type, and data of this type represent in some sense a quantum state, even in the situation where these data are encoded in a classical algorithm. If you would like really quantum data, fully quantum data, in this case, we should have quantum algorithms and quantum resources. And after that, we need a quantum algorithm to process this data. Does this answer your question? Any other question? So the first part, it's about partial trace regression and round cross decomposition. So here we are sitting classical data and classical algorithm. And the main idea is to show how concepts were studied and developed in the field of quantum computing, quantum information, can be useful to improve classical machine learning algorithm. And the two concepts here is related to the notion of partial trace for quantum system, which can be used to quantum system, and to reduce quantum system, and also the notion of quantum channel and lower rank cross decomposition of this quantum channel. So this work was published at ICML in 2020. Okay, the starting point is a regression problem, and more precisely is a trace regression problem. So it's a standard linear regression problem. So if you are familiar with linear regression, this is also a linear regression problem. We have here X is the input, Y is the output is a scalar, and the model is trace P transpose X plus epsilon. So the parameters of the model is matrix P. So what is the main difference compared to the standard linear regression is that the data here is not a vector, but is a matrix. The standard, we have X is a matrix, and we have here the inner product. The trace here is also an inner product, but an inner product between matrices. Okay, and the goal is to find the matrix B. So considering that the input data are matrices, so this can be natural in different situation depending on the data you have. For example, when we are working with spatio-temporal data, we can have, in this case, spatial information and temporal information. Also, we can work on covariance descriptors, and in this case, also the input is a matrix. And the goal is to design a regression methods which is adapted to the situation where the input is a matrix. The output is a scalar. So one known way to solve this problem is a low-rankers estimation. So how to obtain the solution in this case is we minimize a loss function. We can take the quadratic loss function as usual. This is this term, so yi minus the trace of beta transpose xi, and we have the square. This is the square loss function, and we can add a regularization term. In general, so we can add here norm 2 of the vector, norm 1 of the vector, and we are in the situation now where the parameters are matrices. I put here norm 1 to say that this is the nuclear norm. The nuclear norm is the sum of the absolute value of the singular value of the singular value of the matrices. Okay. Why it is low rank? Because this constraint, in some sense, will favor to obtain a matrix B such that the rank is small, and the goal so to obtain an estimation. And this term allows to have better generalization since it is a regularization. There is also some works with which try to remove the constraint, the low rank constraint, and replace it by another constraint here about the positivity of the matrix. So before I have lambda nuclear norm of beta B, and here now we don't have this term, but we consider that B is a semi-definite matrix. Okay. Why it is important, this trace regression problem? Because many applied problem can be formalized using the trace regression problem. Here I mentioned some of this problem. Matrix completion, widely known problem. So we have matrix and we have different missing values in the matrix, and we would like to recover this value. Phase retrieval, widely known problem in the field of signal processing, can be also cast using trace regression. In the quantum setting, quantum state tomography, where the goal is to find the quantum state of a quantum system from different observation. In this case, also, this problem can be written as a trace regression problem. I will not give all the details how to address this problem, but just to mention clearly the relation between the matrix completion and the trace regression problem, I here put the minimization problem we solve when we would like to have matrix completion. So here we have a matrix B star. In the matrix B star, we have missing values, and we would like to recover them. So one widely known way to solve this kind of problem is to solve this optimization problem. So PW is a mask such that we will take into account only the not missing points, and after that we add a regularization about the rank of the matrix. Having a matrix of low rank will allow us to recover the missing points, since this means that we have a strong dependency between the lines and the columns of the matrix. This problem is exactly equivalent to this following one, where here the input is the matrix EIG, so it's matrix about the position of the missing point or not missing point. So here we have a matrix such that we have 1 at the position IG and 0 otherwise, okay? And this is the value of the matrix B star. So solving this problem, which is trace regression problem, is equivalent to solving the matrix completion problem, okay? This was our starting point. And in this work, we try to we extended this framework to the case where both input and output are matrices. and we call it our framework, our regression model, partial trace regression. I will show why partial trace. So first, what is the motivation? So regression problem where both input and output variable, and here is illustration where we can have this problem. So one widely problem in machine learning, we can find it also in language processing, is domain adaptation. What is domain adaptation? So in many situations, we have training data and test data are generated from different data distribution. So here, for example, we have blue data, which are two classes, classification. This is trained data. If we would like to solve a classifier, we can find this separation. But if we apply it to test data, this is the red point, it is not working good because the distribution of test data are different from the one of training data. So one possible solution is to mix the domain of training and test. And this can be done using transferable examples. So in some sense, we will generate new data points such that we can have on one domain for the training data and test data for the two classes. After generating this transferable example and this transformer example, we can now have a classifier on the transformer example, which will work good in for training and also for testing data. In many situations, we can have also data which are, for example, EEG data, and here an example of data such that what kind of the feature we can consider is covariance matrices. So we have EEG data, but most of the classifier will take as input the covariance matrix of computed from this EEG data. And in this case, so each data point here is a matrix, and when we will generate a new data point, it will be also a matrix. And this matrix can have some specific properties like covariance, it is a PSD matrix. Here in this work, we use concepts like partial trace, completely positive map, and cross decomposition. All of these concepts are widely known in the field of quantum information and quantum computing, and we show how these concepts are useful to deal with the regression problem when both input and output are matrices. Okay, some notation I will use. So MP for a matrix of size P by P. MQ, so this is a block matrix. So we have a P by P matrix, but each element of this matrix is also a matrix of size Q by Q. And also I will use the notation LMPMQ. This is the linear map from a matrix of size P by P to a matrix Q by Q. In some sense, this generalizes the notion of matrix. A matrix is a linear map which transform a vector to another vector. Okay, here we have mapping which transforms a matrix to another matrix. Okay, trace. So the trace is a widely known operation. When we apply it to a matrix, we compute the sum of the value in the diagonal, and we have output as scalar. Now we have in situation when we have a block matrix and we apply the trace. So we will do the same thing. We sum all the value of in the diagonal and we obtain a scalar outputs. The using trace in this situation does not take into account the block structure of the matrix. Partial trace is an operation that generalizes the operation of trace. The output of partial trace is a matrix. So the input is a matrix and the output is a matrix. How we can obtain this matrix is by computing the trace of each block. So this point of this matrix is the trace of the block at the position 1, 1. This point is the trace of the block in this position, and so on. So here we compute the trace of each block, and we have an operation that takes into account the block structure of the matrix. Using this operation of partial trace, one can consider the regression problem, where both inputs and outputs are matrices. So here X is matrices, Y is matrices, A and B are the parameters of our model, and instead of having trace, we will have a partial trace. We will allows us to obtain here a matrix transpose. This is the partial trace regression model. Okay. Now the question is how to obtain the parameters of this model A and B. To answer this question, we use the notion of cross decomposition of quantum channel, and this notion of cross decomposition is related also to notion of positive map. What is a positive map? A phi is a positive map if it transforms each PSD matrix to another PSD matrix. So phi is a mapping taking its input in matrix of dimension p by p and outputs in the matrix of dimension q by q. If the input matrix is positive semi-definite, if the output is also positive semi-definite, for each positive semi-definite input, the output will be positive semi-definite. This is the mapping in this case is called positive map. Okay. There is a more strongest notion of positivity in this case, which is called M positive map. It is M positive map. Now we apply the positivity for block matrices. So we have a block matrix, okay, and here we have a mapping phi such that we apply the same. We apply the same phi for each block of the matrix. Okay. If the input here, this block matrix is PSD, the output is BSD, and here we have a block matrix with M by M blocks. In this case, the mapping is called M positive. And finally, stronger notion of positivity, which is completely positive. It is completely positive if it is M positive for any M larger than 1. Here's some example to give an illustration. Transpose. The transpose map. The transpose has as input a matrix and output a matrix. It is a positive map since the transpose of a PSD matrix is the same matrix, so it will be a PSD matrix. So it is positive map. However, it is not too positive. Here is a counterexample. So this matrix, block matrix now, it is positive. We apply the transpose for each block. So here we apply the transpose. This is why we have the 1 here, okay, for each block. And this matrix, it is not positive. It has a negative eigenvalue. So this is a situation where the input is PSD, the output is not PSD, so the transpose is not a too positive map. So it's not also completely positive. An example of completely positive, if you construct your mapping such that we multiply your input matrix by a matrix V and its transpose, this allows you to have a completely positive map. Why it is interesting, this notion of completely positive map? Because there is this theorem known in the field of quantum information, which is the string-springs theorem. So the theorem states that a mapping phi is completely positive if and only if it can be written as the partial trace of AX A transpose. So this is important because our formulation of the problem in the beginning is based on the partial trace and having some similar form. So in some sense, this connects our first formulation with the notion of learning a completely positive map. Having this connection, we can go to the cross decomposition. So cross decomposition, there is this results, very famous results in the field of physics. This result, known as cross decomposition in the field of mathematics, is also known as Choice theorem. Okay, and the theorem said that if we have mapping phi completely positive, then there exists operator or matrices here AG, such that the mapping phi can be written as sum from G to 1 to R AG X AG transpose. R here is the cross of the decomposition or the number of the matrices H. Okay, this is nice because now, since we have our first problem, which is based on partial trace, now we can say that this equivalent to finding this matrices AG. And so we can solve the following problem. Minimize, this is the square loss function or any loss function. The output is a matrix and the input now, the phi of x is a completely positive map, which can be written using the cross decomposition like this. And the goal is to optimize this over the matrices IG. Low rank because we choose here the narrow cross rank is small. Okay, this is a theoretical result showing that the advantage of having a small rank in the generalization performance. I can skip this result. And this to mention, to connect, I started by mentioning the relation between matrix completion and trace regression. So here is a connection also between partial trace regression and matrix completion. And as you can see for this theorem, we can do now matrix completion on blocks of the matrices. We can illustrate, I can go directly to the experiments to show you what kind of result we obtained. So here we consider matrix completion, but when we have blocks which are missing. So this is the original matrix, and now we have different missing blocks. Okay? And you apply after that our partial trace regression to recover the initial matrix. It is well adapted to recover the blocks because the output is a matrix. If we consider the standard method trace regression, we have to recover the entries of the matrix point by point. Okay? And this is reconstructed results. Okay, I can go fast here, but we can find all the result in the paper. So we tried also matrix completion in the situation where we have a different missing point which are not situated in the same place. Before we have blocks missing, this is just entry missing. So we can recover also the original matrix in this case. And also we tried some situation where it is difficult, so we have a lot of point missing, and we try to reconstruct in this case, and the construction is not very good because the problem is really difficult. But what we tried experimentally is to use a kind of a deep cross network. So we added a depth. This is why we mentioned it that depth 2. So we added another layer of partial trace regression, and we added also a nonlinearity. And in this situation, we can recover a good matrix. However, all the theoretical result I mentioned about the connection between completely positive and cross decomposition are not valid in this situation because we have the nonlinearity. Here we induce a nonlinearity. But at least experimentally, it works good. Any question before moving to the second part? Okay. Let's go. The second part is about classical data and quantum algorithm. And this is work with Giuseppe and Mathieu Roger, who is doing his PhD thesis with Giuseppe. And the goal here is to study quantum perceptron. Here I tried to summarize, it's a difficult task to summarize the talk of Giuseppe on 1 or 2 slides. to show the main difference or the main property from quantum computing compared to classical computing. So we have now quantum bit. So instead of having 0 or 1, we can have 0 and 1. So in 1 qubit setting, we have the qubit 0 and qubit 1, which is a vector in C2. And now we have this qubit can be in superposition. So it can be 0, it can be 1, but it can be also alpha 0, 0 plus alpha 1, ket 1. Okay? This is why we say that we have a superposition. This is 1 qubit. If we will go to 2 qubit, we use a tensor product, and now we will not have 2 bases, but we will have 4 bases. For n qubit state, we use the same strategy and many tensor products. And after there is also the notion of measurement, which allows you to go from the quantum world to the classical world. And in this case, when we have a state psi and we measure, we can observe x with probability alpha module of alpha x square. Okay, so if I take the qubit here, alpha 0 0 plus alpha 1 1, when you measure, we will see one of these 2 qubit states, so 0 or 1. Okay, with probability module of alpha square, you will see also with probability module of alpha 1. Okay. After that, we have operations that transform qubit or quantum state to other quantum state, and all the operations in computing are represented unitary matrix. Here, the example of Hadamard matrix. So this is okay, and I'm saying that operation can be done using unitary matrix. Here, for example, this matrix applied to this quantum state 0, we will obtain this is the state plus. So we have equisuperposition between state 0 and state 1. Okay, so to summarize, so instead of bits we have quantum bits. Instead of gates between binary gates like AND or NOT, now we have gates which are unitary matrix. Okay, and after that, reading the output, reading the result, this corresponds in the quantum setting measuring the final state. Grover search. Here in this part, we will show how to apply the Grover search to solve the problem of classification in the context of perceptron. So a classical search algorithm is the following. So if you have a list of numbers and you would like to check if one number is in the list or not, so we have a loop and we have to check all the elements of the list. Okay, what is the complexity in this case? So it is linear with the number of elements in the list. Here the number of elements is big N. Okay, if we would like to we try to address the problem in quantum setting, we can use the Grover search. Grover search algorithm works like this. So we have initialization like uniform superposition. So we have a superposition uniform because we have with the same probability. So this is uniform superposition over all the elements of your list. And after that, all the operation are based on unitary matrix. So we have this Grover iteration. So this is unitary matrix G. I will not give the details of this, but you can look to the slides of Giuseppe to have the definition of this unitary matrix. But the algorithm after that will apply this Grover iteration, big O of square root of n times. And after that, we will measure the results. We can show that we will have with high probability the element we are looking for. Okay, and the complexity here is computed because we will say that the complexity is square root of n is the number of call to the oracle. It's not clear here what is the oracle because the oracle is an operator, is a matrix which is in the definition of G. So the number of apply G. Okay, and the number of times we apply G here is square root of n. So we reduce the complexity from n to square root of n. We have now the classical perceptron algorithm. This is widely known algorithm, and this is the basis of a neural network. So how it works? We have data, training data, which are lablet data. Okay, x, y, y, y. We have an initialization. This is the hyperplane. The perception will find a linear solution to the problem. So we initialize the hyperplane to 0. We can initialize it randomly as you want. And after that, we have a loop. and we will check if your hyperplane will classify correctly all the data. If it is not, this is here, so this is means that we find that there is one data which is misclassified. In this case, we do an update and we have a new hyperplanes. And we repeat this until conversions. So until the situation where we have a W such that all the data are well classified. The computational complexity of the algorithm is linear on n, because we have to verify that all the points are well classified. And there is also another notion of statistical efficiency, more related to generalization. And the statistical efficiency here is equal to 1 over gamma squared. What is gamma? Is the margin of our classification model. What is the margin? Is the distance between your hyperplane and the maximum distance between your hyperplane and your data. So if the margin is high, this means that we can have points in this part of the space and another points in another part of the space. So the problem is easy. This is gamma is high, the problem is easy. If, however, if the two classes are near to each other, the gamma is small and the problem is more complicated. And this complexity, so we have the statistical efficiency 1 over gamma squared. Okay? Now we can ask what kind of advantage we can have when using quantum algorithm to solve this problem. The first way to apply quantum algorithm in this setting is to apply Groover to find misclassified point. Here the classical online perception. As you can see, here we are doing a loop, and the goal here to verify if there is a point which is misclassified by our W. If we find one, we do the update. One can say that we can apply, so this is a search of a misclassified point, so we can apply Groover to find this misclassification. Okay. If we apply Groover instead, we can improve the computational complexity from n to square root of n. So this is the algorithm in this case. As you can see now, we apply quantum search algorithm, searching for a point misclassified. If we obtain a point which is misclassified, we do the update. This is the first way to have a quantum version of the perception. Let's see what kind of advantage. There is extensions of the Groover search to the situation when we have multiple points. But it is true that the first analysis and the first results of the Groover search consider the case where there is only one point, and after that there are different versions, extension of the initial algorithm, and some extension deal with the situation where we have multiple points. Okay. And so if we apply now, if we can try to see what kind of gain we can have here, so we can see that the computational complexity, we can reduce it quadratically, so from n to square root of n. N here is the number of data points. Okay. However, the statistical efficiency, we don't have any gain. There is also another point of view of the perception, which is based on the version space. What is the version space? Is the space containing all the solution. As you know, probably know that the perception, we will find one hyperplane from all the hyperplanes that can solve your problem. So one can consider in this case generating many hyperplanes. So W1 is hyperplane, WK is hyperplane. So we generate many hyperplanes. Okay. If we generate large enough numbers of hyperplanes, we can say that at least one of them is in the version space. If it is in the version space, this means that this hyperplane can solve our classification problem. Okay. And the goal now is to find this hyperplane. So by this approach, we transform the perception problem to search problem, to search over hyperplanes. We obtain in this case this kind of algorithm. We have a lot of hyperplanes generated, and after that we apply quantum search to find one which is in version space. If we find it in the version space, it's okay, we solve the problem. In this case, we don't have computational gain on the number of samples, because when we have the output of hyperplane, we have to check over all the data points that all of them are well classified. However, we have a statistical improvement if here. So from 1 gamma squared to 1 square root of gamma. In some sense, in the first part, we apply Groover to find data. So we apply Groover on data. So we improved the complexity over data points. In this version, we applied the Groover on the hyperplanes. And this is why you have improvement over dependency over gamma. Okay? We can also ask if it is possible to have both advantage. In this case, we can consider some kind of hybrid quantum perceptron, such that we generate many hyperplanes, and after that, instead of looking or doing quantum search over the hyperplanes, doing quantum search over the data points, and try for each hyperplane, check if there is a point which is misclassified. In this case, we can have both improvement on the computational cost and a improvement on statistical efficiency. So to summarize here, so there are different kinds of different versions of quantum perception. The first version of quantum perception here, we have complexity n over gamma squared. If with the first version of quantum, we have improvement over the number of samples. This is why you have here square root of n, but we don't have improvement over the margin. For the version space, we have the improvement over the margin. We have square root of gamma and still linear with n, so we don't have any improvement compared to the number of samples. And the hybrid setting, we have both improvements, square root of n and gamma, compared to the classical online perception. Okay, and we have quadratic improvement. Some simulation before ending my talk. So here the simulation to show the comparison between these different quantum perception with the classical perception. So in blue is the well-known dataset, IRIS dataset. So, and here we are number of operation. We are counting the number of operation compared to the classical perception. And as you can see, if we would like to apply quantum perception setting algorithm in this setting, so to classify IRIS data, it is better to use a classical algorithm. The classical algorithm is performing better for all, better than all the quantum versions. Okay, but this is some sense expected, since IRIS dataset is easy classification task, and one, if we would like to see the advantage of your quantum algorithm in this setting, we have to consider difficult situation, at least difficult for the classical algorithm. This is why we have another data set which we call it hard. Why hard? Because the classical online classifier will do many steps to find the solution, so it's complicated for the classical perception. In this setting, we can see that we have improvements. Using the 3 quantum algorithm, we have an improvement from a computational point of view, and we can see that in the situation where both we have improvement over the number of samples and also improvement over the number of examples, we in this case we can have a better improvement compared to the 2 other versions of the quantum perception. Okay, so concluding now. Yeah, I have 1 minute, so it should be okay. So what we showed here is how to design a new machine learning model like quantum perception, like partial trace regression. These models are based on concepts known and used in the field of quantum computing and quantum information. This concept like quantum superposition, quantum entanglement, low rank cross decomposition of quantum channels. This model also, since are based on solid mathematical concepts, so are enjoyed well-founded theory, and this is promising to design a new efficient machine learning algorithms. By this work, we are in some sense connecting the two fields of machine learning and quantum computing, showing what kind of interaction, good interaction we can have between them. If you would like to know more about our work in this field, we can take a look at the website of our project, QuantumL, which is devoted to design quantum machine learning algorithm and to study theoretically the advantage of these algorithms compared to the classical machine learning algorithms. Thanks for your attention.
Any question? Maybe online first? Questions online? Okay, so local questions? Yes? Yeah, go ahead with your question. So can you go back to the last slide?
Exactly, yeah. Solving the problem to find a hyperplane such that we can well classify all the data points. Yeah, this is a theoretical result about what kind of generalization bound we can obtain. So in the field of machine learning, so important notion is generalization. The generalization means that when we learn a classifier on training data, what we obtain can be useful also for testing for test data which are not used in and so this is no notion. No, I'm sorry, because I didn't find time to explain this, but here the expected risk is kind of generalization bound, means that how our function computed from a finite sample of data points can the risk computed using this function, how is it far from the true risk? The true risk, this is the best function that solve our problem. And in this case, we can have this kind of results, and we can say why you are happy when we have this kind of results. In general, for this generalization bound, we are happy when we have the number of samples in the denominator. This means that when the number of samples go to infinity, so this term will go to zero, and in this case we have an empirical risk which is very close to the true risk, and you know that we have a good function. This is not specific to the quantum setting, and we can have also a generalization bound here. And what is here interesting in some sense is that we have the gamma square, and here we have the gamma. So we have a better generalization bound in this setting. However, this is important, and I didn't really mention it. We can here, so in the iris dataset, we have a better results when using the classical algorithm. We can justify this when you look at the generalization bound. In this, why? Because here you can see that we have the minimum between this term m of s and 1 over gamma s square. Okay, and m of s is the number of iteration the algorithm will do. So if the task is easy, we know that we not need to go to the worst case, and we will converge quickly. Okay. However, if we are in situation worst case situation, in this case we have dependency over 1 over gamma square. Here in the quantum setting, we don't have something equivalent to this m, and in some sense mean that for iris data we are not in the worst case, and so this algorithm converge quickly because we have minimum and ms is smaller than 1 over gamma. In the second situation, we construct a data set that we know that ms will be very large, and so now the algorithm will stop with the dependency over 1 over gamma square, and here we can have the advantage because the quantum setting we have 1 over gamma, so we can converge more quickly. Maybe last point to precise that all these results are obtaining using a classical simulation. So this is why we don't have this notion, because we don't have this notion of error in the quantum computation. Here we have classical implementation, so we cannot measure the running time because we are using classical algorithms, so the running time is not good for quantum algorithm, but we compute what the number of operation will do the quantum algorithm. Let me go to the classical online. So this is the classical online setting. Maybe you can use also the board. So the problem here is linear classification. So linear classification and binary classification. We have two tasks. This is some data points, and we have this data points. And the classify and the perception algorithm is to find a line, hyperplane, a linear function to separate the data points. And how it works, we generate randomly or initialize W to 0. For example, maybe this one is W at time 0. And after that, we verify if the points are well classified or not. For example, this one is not well classified. In this case, we say that this is not a good W, and we will compute a new W, will be W1, which will be equal to W0 plus YT XT. So YT here, so it will be Y0 X0, the first point. Okay? And so on. So after that, so we can have another W like this. Still, there is some error, and until convergence when we find one such that we don't have any point which is misclassified. Okay. So if you have in this situation, you see that we have a lot of hyperplanes such that we can separate the data. If we are in a situation where the two classes are very similar, are very near to each other, we start by one, so we have to do a lot of iteration to find a good one. So the hard data set is constructed such that we know that the classical algorithm will do a lot of iteration before finding one hyperplane that separates the data. One possible, so here we consider only the linear setting, so separable case and linear setting. And if we would like to do some kind of non-linear classification, one possible way, like in the classical setting, is to use, in the field of quantum mechanics, there is two options. First option, this is the first option studied, is to use kernel methods. So in some sense, we find another representation of your data in another space using kernel functions. And after that, in this new space, we apply the linear techniques. And there are some recent work, interesting work, making connection between kernels and the quantum encoding of the data. Because what is maybe, I didn't really emphasize this, if we have, to apply a quantum algorithm, we need quantum states. So if we would like to apply this quantum perception, there is a first step, how to transform your classical data to quantum states, because Groover search will take as input quantum states. And there is this kind of, this step is called quantum encoding of classical data. And the quantum encoding, in some sense, this you transform your data, and we are working in another space, transformation space, like a kernel. So the people say that, okay, depending on what kind of quantum encoding, we are choosing in some sense a kernel function which allows me after that to solve a nonlinear classification problem. We have more chance, but this is true theoretically, because we know that with large, as said by Giuseppe, with large quantum state, we have a problem also with other problem with quantum error and so on. But theoretically, if we have a good quantum computer, which don't have negative impact with error, so in this case, larger is better. Okay, and there is some work trying to do some quantum neural networks. So associating different, in some sense, different unitary gates playing the role of perception. And after that, in this case, it is possible also to learn a nonlinear decision function.
Long live India and France friendship.